In Lecture 15, we're going to take a further look at inverse trig functions. In particular, we're going to find the exact values of expressions that involve the inverse sine, cosine, and tangent functions. We're also going to define the inverse secant, cosecant, and cotangent functions and be able to use our calculator to evaluate those functions. And last, we're going to take a look at writing trigonometric expressions as algebraic expressions. Okay. So to begin with, let's look at finding the value of sine inverse of sine. Now this is a question that we've actually already looked at, so it's familiar to us. We learned that as long as the angle inside here, if between negative pi over 2 and pi over 2, right, then sine inverse of sine cancel each other out and you're just left with that angle. However, 5 pi over 4 is not between those two. In fact, where is 5 pi over 4? Remember, pi over 4 is a 45-degree angle, so 5 of those, 1, 2, 3, 4, gets me back to pi, and then 5 pi over 4 is down here. Okay? And remember, if this is the unit circle, what we're looking at is, since sine of 5 pi over 4, we're looking at the y coordinate of that point right there, is the value of sine of 5 pi over 4, which we know what it happens to be. It's, in this case, negative square root of 2 over 2. Right? But actually, we don't even have to know that to get the answer. Remember, with inverse sine functions, their outputs are always in the right half plane. So if I go straight across to the point on the other side that has the same y coordinate, what's that angle going to be? Now, it would be 7 pi over 4, but remember, we're looking for between negative pi over 2 and positive pi over 2. So it's the down angle. This right here will be negative pi over 2 for that reason. Pi over 4. Pi over 4. I said pi over 2. Pi over 4, because that's negative 45 degrees or negative pi over 4. Okay? All right. Now, in the next question, you're asked to find the sine of a tangent inverse of 1/2. Now, you may not recognize it in this form, but this is the same type of question that we've actually answered in previous sections. In fact, we answered it back in Lecture 10 whenever we had this kind of question. If tangent of some number, we'll call it theta, is equal to 1/2, which is what this right here, that's theta. So we're saying tangent of what angle is 1/2. And in this case, theta, because it's an inverse tangent, is between negative pi over 2 and positive pi over 2. What is sine of theta? Recognize that question? So what we did back in Lecture 10 was we drew a circle, and knowing what quadrant we're in, we know we're somewhere over in the right half plane. Now, if tangent output is positive, right, then we're either in the first quadrant or third quadrant. But because we know we're in the right half plane, we're somewhere up here, right? We know we're in quadrant 1. And we know that the tangent is 1/2. So what we did back in Lecture 10 was we said, okay, remember that tangent of theta is y over x. So let's let y equal 1 and x equal 2. So we're somewhere up here where x and y is 2, 1. Now this is not the unit circle. This is actually some other circle of radius square root of 2 squared plus 1 squared. And that's just from the distance formula. That's square root of 5. And now sine of theta will be y over the radius, or in our case 1 over square root of 5, or if we rationalize square root of 5 over 5. Ta-da! You're able to solve these kinds of questions the same way we did back in earlier sections. We assign an x and a y, find the r, and then use the theorem that relates sine of an angle to any circle of arbitrary radius and the point on the outside. So let's do the same thing again. What does this right here tell us? Sine inverse of negative 1/3 means sine of some angle is negative 1/3. Now, since we're looking at inverse sines, we know theta is between negative pi over 2 and positive pi over 2. And we know that for a circle, we are in the right half plane. And since sine is negative, remember all students take calculus, the function is negative here, and sine is negative in the bottom half, which means I have to be over here in quadrant 4. Theta is in quadrant 4. I can tell that because I know it's in the right half plane and I know sine is negative, so I know it's in quadrant 4. So I'm going to have some point down here. I'm going to remember sine of theta is y over r. So we're going to let y equal negative 1 and r, which is always positive, be 3. Okay, so remember that we can then find x by using x squared plus y squared is equal to r squared. So that's x squared plus a negative 1 squared equals 3 squared. So x squared is 9 minus 1, or 8. So x is square root of 8, or 2 square roots of 2. And we know it's positive, right, because I'm on the right half plane. So x has to be a positive. I normally would have to put a plus or minus right here, but we know it's positive because of where the angle is. It's in quadrant 4, and x is positive for quadrant 4. So then what does cosine of theta equal? It's x over r, which is 2 square roots of 2 over my r, which was 3. So the final answer is 2 square roots of 2 over 3. Okay, we do one more. We're going to find the exact value of tangent of cosine inverse of negative 1/3. Since we're doing cosine inverse, we know we're in the top half plane. Cosine of theta is negative 1/3. And since it's negative, we know we're over here, right? All students take calculus. Cosine's positive up here where it says all, and down here where it says C. So it's negative over here. We know we're somewhere over here for our angle. We never even have to find the angle. That's the good news. We just have to say let this be x. So x is negative 1, and let this be r, which is 3. So x squared plus y squared equals r squared, tells me negative 1 squared plus y squared is equal to 3 squared. So y squared is 9, and then move the 1 over the other side, minus 1, 8. So y is 2 square roots of 2 again, because you take the square root of 8, you get 2 square roots of 2. You know it's positive because we're in the second quadrant, and y is positive. All right, and then tangent of theta would be y over r, which is 2 square roots of 2 over, not y over r, y over x, my bad. 2 square roots of 2 over negative 1, or negative 2 square roots of 2. Again, we knew we were in the upper half plane because that's the output from cosine inverse. But we go through that same process as we did on the previous examples, and we can find the output of that trig function value without even having to know what the angle was. All right, now let's move on and take a look at, and we're going to go through these relatively quickly because they follow the same basic structure as the inverse sine, inverse cosine, and inverse tangent. We talk about the inverse secant, the inverse cosecant, and the inverse cotangent. I want you to notice that the inverse secant has outputs just like inverse cosine. Which makes sense because cosine is 1 over secant, or secant is 1 over cosine. On the other hand, these two, well, the next one, I should say, not these two, we've got to be careful. Cotangent is a little bit trickier. Cotangent behaves actually like cosine. This is like sine inverse here, but cotangent behaves like inverse cosine. Now the reasoning is not hard to see. You just got to go back and think about I want to hide my ribbon. There we go. Sorry about that. So the reasoning here is that secant, if you'll remember the graph of it, since it's 1 over cosine, this was cosine. So what happened was secant looked like this. I did that wrong. Try that one more time. It's 1 over cosine, so I draw the cosine function, which looks like, oh, I did that right. I need to pay closer attention to what I'm doing here. Alright, so secant was this guy and this guy. And notice if I went from negative pi over 2 to positive pi over 2, I would have a non-one-to-one function. So what we do is we restrict the domain and look at this piece of the curve all the way up to here. And so the restriction is from 0 to pi, just like with inverse cosine. If I did 1 over sine, sine looks like this. So the graph of cosecant looked like this. It was these upward U's, just like the secant was, only it shifted over. And again, if I went from 0 to pi, I would have a non-one-to-one function. So what I end up doing is restricting the domain. So I look at this part of the function here all the way down to this part of the function here. So restricting here to here, which is negative pi over 2 to positive pi over 2, will give me a one-to-one function. And now cotangent, here's why cotangent behaves like cosine inverse instead of tangent inverse. Cotangent as a function, when you graphed it, looked just like tangent, only it was upside down and shifted. So you went from 0 to pi, and instead of starting low and going high, you started high and going low, right? That's the cotangent function, right? Now 1 over that would have asymptotes We can just look at the picture here. I don't have to go any further than that. I'm going to have to pick one of these curves, and this particular curve right here, you'll notice, is 1 to 1 if I just use one piece of it, so I restrict the domain from here to here, which is 0 to pi. Alright, I probably spent a lot more time explaining that than was necessary, but the point here is how these things look compared to the other inverse trig functions. And here's an illustration on the next page to see that where you get the outputs are in which half plane and where the inputs come from. Because the output of a cosecant is always bigger than 1 or less than -1, that's the only thing you can plug into the inverse for both cosecant and secant. And then inverse tangent and inverse cotangent, you can plug in any number into them, but for inverse tangent, the output is always in the right half plane, and the output for an inverse cotangent is always in the upper half plane. And again, the reason was on the previous page, or I guess the top, yeah, no, the previous page, right here. All that scribbling that I did there. Okay, sorry, let's move on and look at some examples. The easiest way to handle inverse cosecant, inverse secant, and inverse cotangent is to use the quotient identities. Namely, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. Use those to convert the problem to a sine, cosine, or tangent question. In this case, what you see is, let's say we've got cosecant inverse of 2. So cosecant of something is equal to 2. Let's say theta. Now cosecant is the same thing as 1 over sine of theta is equal to 2. So divide the 2 across and multiply the sine across. What you end up with is 1/2 is equal to sine of theta. Now we're looking at, again, because we're doing cosecant, cosecant behaves like sine. We're looking at the upper half plane. So we're in the positive area. Our sine is what angle gives me a 1/2 height, and the answer is theta is equal to pi over 6, which I can pull off my unit circle definition. 1/2 is the sine of pi over 6. The same thing's true if you actually can't find the angle exactly, but you need to go to a calculator. You'll find in most circumstances your calculators do not have a secant inverse, a cosecant inverse, or a cotangent inverse. But they do have the arc cosine, or inverse sine, arc sine, or inverse sine. So you can just convert this. This says secant of theta is equal to 3. Right? And then 1 over cosine of theta is the same thing as secant. So we're looking at what angle gives me a 1/3 when I take the cosine of it, which, by the way, is the same question as cosine inverse of 1/3. Plug that into my calculator, and I get 1.23 out of it. So with secant, we're going to use cosine inverse. With cosecant, we need to find a way to write this in terms of sine inverse. The reason being that you want the same domain, or actually the same range, the same output values. That's going to become an issue down here on C and D that we got to be careful with. So with cosecant inverse, we'll rewrite this as cosecant of theta is equal to -4, which means 1 over sine of theta is equal to -4, or -1/4 is equal to sine of theta, which says theta now is the sine inverse of -1/4. So I'm going to use my calculator, plug that in, and I get -0.25 as the approximate value for theta. So that is the same as the original problem. Perfect. Now with cotangent, we can't use inverse tangent because it's got a different range. So we have to somehow write this in terms of cosine inverse. So how do we do that? Well, we have to figure out what is if we know the cotangent of the angle, we got to figure out what is the cosine of that same angle. So this says cotangent of theta is equal to 1/2. So looking at the unit circle, looking at a circle, we know we're in the upper half plane because we're in tangent. Since it's positive, we know we're somewhere over here. We're going to let R be 1 and not R, sorry. Erase that. We're going to let X be 1 and Y be 2 because cotangent is Y over X, which means R is the square root of 1 squared plus 2 squared, which is square root of 5. So what's the cosine of that angle? If cotangent is 1/2, the cosine of that angle is X over R, or 1 over the square root of 5. So with my calculator, I'm going to use cosine inverse of 1 over the square root of 5. I got to go through this extra step here to get it in terms of cosine inverse so that I can plug that into my calculator, which gives me a 1.11. Again, the reason why you have to use inverse cosine is so that you have the same range, the same output as the inverse cotangent. Inverse cotangent does not have the same range as the inverse tangent, which is what we'd be tempted to use otherwise. Okay, so let's try the same thing again. We know cotangent of theta is equal to -2. Okay, which is -2 over 1, so we're going to let this be X and this be Y. You got to be careful and make sure we've got the right sign for those, meaning SIGN, sign. Since we're in the upper half plane, we know, and we're negative, we're going to be over here somewhere. So X is negative and Y is positive, so we can use X is equal to -2 and Y is equal to +1, which makes R equal to the square root of -2 squared plus 1 squared, which is square root of 5. So cotangent, sorry, not cotangent, cosine of theta is X over R, or -2 over square root of 5. So theta is cosine inverse of -2 over square root of 5, and go to my calculator for that. .68. Done. All right, as we wrap up this particular lecture, I wanted to point out one interesting little result that can come from the process or technique that we've introduced in this section. In particular, if you look at something like sine of tangent inverse of u, we've gone through solving this where we had a particular value in here for u. We can repeat that same process using a general parameter like u in the problem, and the result will be that this is equivalent to an expression, an algebraic expression, that depends on u but actually has no trig function values involved at all. Notice this. If you think of an inverse tangent function, you know we're going to be up here in the upper half plane. And fortunately, sine has the same range, so I'm going to be able to plug this right back into the sine function. It doesn't really matter where I am. You could be positive, you could be negative, you could be anything, since I can plug any value into tangent u. Let's say it's over here, just for argument's sake. Let's say I've got tangent of some theta is equal to u. Now if I write that as u over 1, I can call this top value x, which could be positive or negative if I had chosen the point on the other side. And let's let y be this guy. Okay, and that's the coordinates of this point. And again, it would work the same as if I had arbitrarily chosen a point over here. I would just let this be u comma 1 now, right? So using the fact that tangent of theta by definition is x over y, we're going to use these two values, which we then use this formula, or without the square. R is the square root of x squared plus y squared, so it's the square root of u squared plus 1. And what then is sine of theta? Sine of theta is y over r, which is 1 over the square root of u squared plus 1. This is equivalent to that. Notice for any u, tangent inverse of u, and then take the sine of that. So sine of the inverse tangent of u is always going to be 1 over square root of u squared plus 1. For any u. That's the algebraic expression that's equivalent, that it doesn't contain any trig functions whatsoever. Thought that might be interesting. Throw that in there. You might have a problem or two in your homework regarding that. With that, that is the end of lecture 15.